Morning, everyone. Good morning. Thank you, first of all, for coming today. My name is Nicolò, actually, and I am responsible for the renal genetic testing in the research lab. And as you can see, I'm not from North Dakota. 2 years ago, during my first presentation, I noticed two types of people here. The ones that were dozing off, and others having an expression like that. So I do apologize for that, and the good news this time is that I have only 15 minutes, and I completely changed my presentation. So I won't use the same slide as last time. So let's get started. So what you see here is a fantastic meal and our final genetic report. What's the link between the two? They both represent the culmination of a process, the cooking process and the genetic testing. And what is missing in this picture is what is behind that. It's behind that there is an entire process that is, I would say, challenging, and for most of us, it's unknown, remains unknown, because let's say the truth. It doesn't arouse so much interest, what we are doing when we do the genetic testing. So, because sorry, still fighting with the language. So one thing is that the fact that it doesn't arouse so much interest, it's the reason why I'm here, just to shed some light on what is this process, what happened behind the scenes. So as I like food, I like cooking, I found a lot of similarities with our work, basically. So imagine that our lab is an upscale restaurant. And imagine that our benches, where we work, it's the kitchen of this restaurant. Like any other good restaurant, there are like a selected menus. And we have our main course. Our main course is represented by the genetic renal panel. It's a panel of 11 genes, okay? All of them are known to be associated with the TMA. Richard presented some of them. We have, do we have a pointer? No. So we have complement genes. The first 6 are the complement genes. Which are responsible for a complement-mediated atypical aHUS. We have 2 genes that belong to the coagulation system, which is THPD, thrombomodulin and plasminogen. And we have also DJKE, which basically is associated with a pediatric onset of atypical aHUS. But we have also 2 other, basically 2 TMA genes. So one is ADAMCS13, responsible for the thrombotic thrombocytopenic purpura, which basically can overlap the phenotype with atypical aHUS. And we had lately this last gene, MMA-CHC, which is methylmalonic aciduria with homocystinuria. We had this one because also this gene, aHUS, can basically, the phenotype of this disease, which is a vitamin B12 defect, can overlap the phenotype. The genetic testing process is a 3-step process, basically. The first step is when we basically extract your DNA, we process and we sequence. The sequence means we read your DNA, what is inside your DNA. The result is what you see there. It's a raw data. It's a file. It's a computer file, actually. I call it jumble because, you know, it's a mix of letters and numbers, okay? But guess, exactly in the restaurant, what we have here, we receive the order in the kitchen and we start to process the order. We cook. We mix the ingredients. And what we get is something that is raw plate. It's not a finished plate. So the next step will be to analyze this data. So we need, for sure, to basically turn what is that raw data into something that is understandable to us. So we need all the information that are inside that file, because it contains all the information of all the genes that we screen. And then, thanks to the bioinformatician, we are able to get this product, which is another intermediate step of the process. Again, in the kitchen, what happened? We can't present a plate like that. So we need to be transformed. We need to make it more presentable and more appealing, I would say. The last step is the interpretation of your results. What happened? We basically gather during our weekly renal meeting, we gather all together. There are almost, I would say, 20 people. We get all the results from the genetic part, but also from the functional teams. Basically, we get all this information for each patient. So basically what we do is we discuss the result of each one of you in details. And again, using this, and I'll continue to use this analogy, before sending out the plate, we need that the chef take care, basically have a look at the final, would say, check of the plate. But one goal, the main goal of the genetic testing is basically to detect DNA variants that could be related to the disease. But the problem is that the genetic variants are basically do not behave in the same way. What I mean, I will try to explain with something that is probably not so scientific, but let me explain with a recipe of the tiramisu, that's concept. If you want to make a good tiramisu, what you need is 100 grams of sugar, okay? If the recipe that you use has somehow a typo, okay, instead of 150, you use 100 because it's written 100, what's going to happen is that your tiramisu will remain good, it's still good, nothing going to happen. There is no change. That's what happened in our DNA, in the DNA, and specifically in a gene, okay? If there is an alteration, that kind of alteration do not alter the final product, okay? Imagine your factor H. You have a variant that is really, really common. So most of you have this variant. Nothing going to happen. What happens if the typo in your recipe is bigger? For example, it's double or half the size. Well, what we would have, what we would call a slight variation, so a minor change. It could be a deterioration. It's too sweet. Or you could have like an implementation, right? Oh, I prefer this with less sugar, okay? And this is quite common. It's a variant that this alteration, it's not so common like the previous one, but it's common, assuming 1 out of 50, for example. But what happened if the typo is really big? So instead of we had 1 0. Yeah, sorry, I put question marks because you know, someone can find this eatable, but not me. But anyway, so what happened if the alteration is big? We have what we call mutation. Okay, it's something that happens really rare, and that's what drives the disease. But to understand, so it's. I understand that atypical aHUS is not like a recipe of a tiramisu. I totally understand that. But because when we talk about atypical aHUS, we talk about a complex disease, a multifactorial disease. Basically, when we identify a variant, this variant not necessarily is the cause of the disease. It could be something that can predispose the disease, because it has been demonstrated that there are multi-factors that precipitate the disease. you could have a mutation, a variant that predisposes the disease. You could have another variant that can increase the risk of developing the disease. And then what you have, the triggers, pregnancy, virus, anything. If you put all together these things, basically you will go over a threshold and you're gonna develop the disease. So how can we detect, or how can we basically get all this information all together? So when we identify a mutation, a variant in your DNA, what we have to follow, there are guidelines that tell us what we have to do. So for example, let's be clear. We find a variant in factor H. Okay, the first thing that I do is, first of all, check if this variant is published in any paper in the literature. And I have to be very careful because long time ago, some variants have a different nomenclature. So it's going to be different. After we see that, it's what kind of other information I can get. Let's see, there are any functional studies that's going to tell me that this variant can cause some trouble? And we have to look carefully at that. But it's not sufficient because then we have to see and we have to ask ourselves, how frequent is this variant? How can I say it's frequent? I go online, there are very useful database, population database control, where I can check this variant and see how many people, normal people, could have this variant. If it is really frequent, I start to doubt that the variant that we identified is somehow associated with the disease. Perhaps it's something else, but it's not that one. Not only these three, but for example, we need we use also what we call in silico software. So it's like a predictive software. You put all the information in the software through very complicated algorithm, put out a result. And it's basically another hint. And finally, it's really important, so this one, patient clinical information. We have to know if this variant, for example, segregates in the family. So if someone else in the family has the same disease and then has the same variant. And this is important. It's a very important hint. But most of the time, unfortunately, we are not so lucky to get some clinical information. And we are missing basically pieces. When we get all this information, and back to our step 3 during the interpretation of your result, here is what we get. A final report with all the information taken all together. The last slide is about the importance of the genetic screening, okay? I said it's complicated, it's challenging, but it's still important. It's important, first of all, because support the diagnosis of atypical aHUS. So this is important. You don't make a diagnosis with the genetics, you support the diagnosis, okay? The second is that it can give prognostic information. Some genes have a particular behavior, okay? So it's good to know if which gene is affected. Then it helps also to guide the treatment. Think about the JKE. If you have mutation in this gene, probably eculizumab won't work. But in any other genes, yes. And this is very recent, actually. Richard gave me the paper like 2 days ago about the treatment with eculizumab and basically stop the treatment. Well, from this data, basically what happened is that if you have mutation in factor H and MCP, it's the discontinuation of the treatment is not so recommended due to the multiple relapses that these patients have in these studies. But however, in the future, for sure, this is gonna be really helpful. And finally, the suitability for a possible transplantation. If you want to give, for example, a kidney, that's important to know if you are carrying a mutation, because you can transfer the mutation and you can basically develop again the disease. So I would like to thank you, Master Chef Richard, for giving me all these possibilities here, but also the entire, this is just a part of our people in the lab, and thank you so much. And I'm happy to take any question, perhaps if it's not now, also later during any breaks. Please feel free to ask me everything.